All right, so in order to do this, first thing we have to do, right, to check whether conditions for performing inference are met, you got to know what the conditions are. So let's talk about that real quick. Conditions for inference. And let's also talk real quick about the sampling distribution of slope. So before we can get to this problem, let's look at the. Okay. All right. So we're gonna have some. I'm not gonna write predicted y like the book does because I can use that. I can make a symbol for that, right? Y hat. And if we have some alpha plus some beta x, and we let b, the letter b, be the slope. Then we're going to have our mean is going to be the mean of b, we should say. Sorry, the sampling distribution. Oh, two equal signs, that's extra. What does that say? That says that the mean of the sampling distribution of b is the slope, right? It's just a formal way of saying that our mean is the slope. And then our standard deviation of the sampling distribution of b is going to be sigma sub b equals sigma divided by sigma sub x times its derivative. This formula, this particular version of this formula is not given to you, but another version is. So let's talk about that. So on your reference sheet, there's a very strange version of this, and you can kind of decipher what's what from it as we go on. We'll look at our. So I'll bring up your formula sheet here. Huh? Yeah. It's the. No, so B1 is our slope, right? Yeah. And the standard deviation of B1 is at S sub B1. And it's quite strange. In order to make that look the same, you would actually have to do something. Really strange. Good news is, the chances of me having to use that are fairly slim. Because, for the most part, you'll be given a mini-tab output that will have your standard error of x, standard error of your slope and whatnot, right? So, sorry, standard error of y and standard error of your slope. So, that is the good news. So we can say that the sampling distribution is approximately normal if it meets the conditions for normality, right? And we're talking about normal. So if our x value is greater than 30, that counts, and so on. Moving on, let's talk about conditions. Yes. So let's look at conditions. For regression inference. I wish I could have found an image of this somewhere. I'm going to draw it as best I can. I think this is an important picture. And I'm not doing a good job of this picture. All right, so this is an interesting picture. It's kind of weird. It's three-dimensional, right? It's like imagine you have a XY coordinate plane, and then sticking up out of it, right, is a normal distribution. That's what that's supposed to look like, okay? So what we're saying is that the sampling distribution of B follows the normal distribution if for each x coordinate that we have, right, along our line, our outputs, our y values are normally distributed, right? So you could imagine there are all these y values kind of stuck in here, right? And we find that those are actually normally distributed. And it's just a really nice picture of it. I like that picture. It helps me understand it. So we get a new acronym. Liner. So linear minus the A. Pretty easy to remember, right? So the L actually stands for linear. Is it linear? So we got to check if it's linear. How are we going to check if it's linear? We'll look at a residual plot. If it's not linear, then we'll transform it, and we'll learn how to transform it in 12.2. All right. So is it linear? Look at the residual plot. Do you see a pattern? Right? Does it look like there's some weird curvy pattern? Do you have like a block over here and a block over here? Right? If you see any sort of pattern, then you're going to question whether or not it's linear. I stands for independent. At this point in time, you will check this condition. Right? That is your 10% condition. N stands for normal. None of these are too far from what we've been doing, right? And what we're doing is we're saying y varies according to a normal distribution, right? And that's what this That's what this picture tells us, right?
Yes. This case,
Yeah, sorry, I only see that. I only couldn't see that. Sorry. I don't know why I get this one memorized. Yes, that's right. Sorry. No, no. Thank you. And again, that's what the picture tells us. All right. This is a weird one. Equal standard deviation. So this is different. We're gonna say, and I'm probably gonna need a little more room. Standard deviation is the same for each. I'm trying to abbreviate this so I'm not. Yeah, we can do this. Sorry, I can't abbreviate. I figured it. So we could say S of y, right? The standard deviation of y is the same for all values of x. And then R is random. The data comes from a random source. All right, well, now we're ready to answer the questions. Let's go to it. Let's check our conditions. L. So I would actually go ahead and do a little extra, right, and actually describe it. I would say there appears to be I don't know about the strength, so I'm not going to say anything. I'm not sure about the strength. I'm going to make a guess. Well, moderately? No. Let's go. A negative linear relationship. Between row and score, right? Again, putting that into context. Okay, I, independent. I need to give you what n is, and for some reason, it's written like much later in the example. So I could, so, n equals 30. And we're trying to generalize this about all classrooms, right? So we could say it's safe to say that there are more than I'm just going to put 10 times 30. So that it's kind of clear what I'm doing, right? That I'm actually doing the 10%. All right. L-I-N. Normal. All right, so we were missing our normal probability plot. This is going to be the best way to determine that this is normal, right? It follows a fairly linear pattern for our expected p-score. So that's so let's say and this one's weird because if we're looking at this in terms of the idea of that picture that I wrote, right, with the normal distributions along the least squares regression line. Yeah, I mean, there's no way with what I've been given here, a bunch of graphs. There's no way for me to know what's going on with this. So let me show you a picture of what it shouldn't look like. It should not look like this. So I have some Y and some X. And imagine we had a line that looked roughly the same, right? So if I have a pattern like that, right? Where it looks like it's fanning out. This standard deviation is definitely not going to be the same as the standard deviation, right? As my x values increase, my variability in y is increasing, right? And so we would say that would, if we had a graph that looked like that, it would violate our conditions for inference, right? And likewise, right? So if I had something, let's see. Yeah, so if I had something like well, darn it, they might offset each other. Right, that's looking weird, right? What we're trying to determine is, based on the plot, does it look like the variability in y is changing, right? as x increases, does the variability in y change? It looks like, right, our variability in y right here is very small, while our variability in y here is very large, very small, then very large, so it's changing. We're getting more of a spread. So that's what we're looking out for. And then do we see anything like that? In this case, we don't see that, right? It looks like, you know, if we're looking at this distance to this distance, is that very different from this distance to this distance? The variability is not super high as we go, or it's not whether it's high, but it's not that different as x increases. Our variability is staying fairly constant. Not exactly, of course, but fairly constant. So that's what we're looking at when we're talking about equal standard deviation. So we would say as x increases, the variability in y stays relatively constant, we could say. Take a look at this. All right, we got our line. There is no A, right? Good news. So now R, random, right? The data comes from a random sample. That's the easy one. Cool. Is that all we were asked to do? Just check where the conditions are met. All right. And just real quick, while we have this is the least squares equation, right? Regression equation. So let's interpret our slope and our y-intercept, just because it's been a little while, and we should. So the y-intercept is 86. Tells us that at row 0, so if you were right next to me all the time while I was teaching, like row 0, right? You should get an 86 on the test. It might be strange, but you'll get a B, right? And then more importantly, interpreting our slope. So we expect that for each increase in row, we expect that for each increase in row, there should be a 1.12 decrease in test score, right? So that's the way we would interpret that. In context, all right. You get a lot of stuff. And now we're here. Okay. So we get to look at some Minitab outputs that we had not used before, right? The one that we really need is this. We actually get a T test statistic here, right? So this is our test statistic there. And over here we get a p-value. We'll talk about that as we go. Because I want to be able to. But anyway, so we were just living in here before, right? We were using this. We were using this value, and that's it, right? Those were the only values that we were using from a Minitab output, right? Where This is our y-intercept. That's our slope. We get what r squared is, and from that we can find our r value by taking the square root of the decimal value of that number. So we can find our correlation. Okay, so the standard error of the slope, SE, so remember, this column, everything in this column corresponds to your slope. Right? I mean row, sorry. I guess I couldn't say the row. So my brain went to some other word. But everything in that row, named row, corresponds to your slope. So then this is the standard error, or the standard deviation, right? So let me get this wording right. Make sure it's perfect. All right, so if we're going to interpret this value, so if we were to do this experiment, or if we were to do this, I'm trying to get the wording right in this thing. If we were to take repeated samples of this size, the slope should vary by 0.9472, right? From the true regression. I'm going to write this down. So it assumes that somewhere out there in the universe, there is a regression line that perfectly models this out. But we're kind of saying that there is, right? We're about 0.9472 units away from it. We are definitely not going to have time to do this interval, this confidence interval. We'll at least get the setup down for you. Okay, or maybe we can. I was wrong. We can do this. So remember, your confidence interval is going to be, it's always, right? Your parameter. plus or minus your critical value times your standard error. So we're going on slope, right? So, and remember, we're looking at the sampling distribution of B, right? What's B? It's our slope, negative 1.1171. All right, our critical value. We're going to use our T star statistic, right? For this. We would use C star if we knew the standard deviation of the actual population, and we don't. So we have to go to T star. Our degrees of freedom should be 30 minus 1. 30 minus 1. And let's talk about that real quick. And that's what I had written here. And then our standard deviation, our standard error of our slope is the standard deviation divided by standard deviation of x times the square root of x. And again, this is a version of the equation that I gave you, another version of the equation that I gave you. I showed you on your formula sheet. All right, so our degrees of freedom is going to be n minus 1. N minus 6. So let's apply that to this particular problem. Oops. All right, so if we look at our T table, our degrees of freedom, our degrees of freedom is going to be 30 minus 2, or 28. If we look at 20 degrees of freedom, and we're looking for 95%, we get a T star critical value of 2.048. And now we need to calculate the standard error of B. I'm sorry, we don't need to calculate it. It's been given. Thank goodness. We do have a formula, but it's been given. It was 0.94722. And we calculate this, and we get you get 1.1171 plus or minus. Our standard error will be, or our margin of error, I should say, 1.9399. So our confidence interval is equal to negative 3.0570, 0.822. We got through this problem in our last class. We found our confidence interval. We did not interpret in confidence. And remember, we're actually performing inference on the slope. So we're looking at the slope of this least squares regression line. So we're going to say we are 90%. Where were we at? 95%? Okay. Do I want to say versus? I don't want to say versus. I want to say. So, or instead of for, we could say relating. Would be a good word to use here as well. All right, and this is a really important. How do we interpret this confidence interval? How are we going to interpret this confidence interval? It's talking about our slope, right? So let's go back to our graphs. It appears that, right, as this is what the teacher was trying to find out, right? Do students who sit further away get lower test scores, right? And we have this least squares regression line that kind of shows that pattern, right? As your row increases, your score decreases, right? But when we construct the confidence interval, we're going to say that we're 95% confident that the true mean. Sorry, you keep saying mean. Sorry, that the true slope is in this interval. Well, unfortunately, right? Our values over here at -3 all the way up to 0. It looks like the relationship that she wanted is happening because there's a negative slope, right? But 0 is included, and some positive values of slope are also included in this interval, which means that it's also possible that as row increases, scores increase, right? Which would say that probably there's not a negative relationship between row number, right? Distance from the teacher, or distance from the front of the class, and scores. That makes sense? So that's how we're going to be interpreting these. We're going to say, hey, if our slope was negative, then the relationship that we want looks like it's happening, right? If we have convincing evidence that the slope is indeed negative, then the relationship that as row number increases, or distance from the teacher increases, scores decrease, we have convincing evidence that that's happening. This sentence I just said was malarkey. It was all backwards, but it wasn't malarkey. It was not good. All right, so let's go ahead and do another one where we're going to perform a confidence interval. We're going to do some inference on slope. All right, so we got bunches and bunches of data. Bunches and bunches of data. We got so much stuff to look at. By the way, this is a lot like what a question 6 would look like, right? You're going to get a lot of stuff. You're going to be asked a bunch of, actually, sorry, I was thinking of the next one. The next one that we're going to do is a lot like question 6. This is like a normal standard question, sorry, where we're going to have to construct a confidence interval. We've been given lots of data. We're going to have to interpret it. So here we go. We got some Mentos. And the data looks strange right away, right? I took a pause because I looked at that residual plot, and I said, huh. Is there a pattern in this residual plot? I don't know. I would have actually liked to have seen a normal probability plot for this, just to see if the data is normal. But we have enough here to do this. All right. So we know the whole Mento trick, right? They spew soda because of the carbon dioxide that's released. And I want to get through more. Here we go. So they're dropping either 2, 3, 4, or 5 Mentos in a randomly selected bottle. Awesome, I see the word random. Waited for the fizzing to die down. They measured the number of cups remaining in the bottle. Then they subtracted this measurement to figure out how much was expelled. So here's our data. It's going to look a little strange because we're going to have repeating x values, right? That are going to give us different y values. So that's why the data looks a little weird. It looks a little different. Because rather than just going 1, 2, 3, 4, 5, 6, 7, 8, right? In a nice sequential order, we've done multiple of 2, multiple of 3. So I saw this residual plot and I said, well, it looks like a pattern, right? But really not. It doesn't look like a curved pattern, at least. So I don't know, when I'm looking at these things, I try to notice things like that immediately. And this one, a red flag came up, but then I thought, okay, well, what's going on? There are these multiple x values. So of course it's going to have like a weird looking pattern to it. But it's not a curved pattern, which is okay. So let's go ahead and go through this. So we're looking for the slope. We're going to perform regression on the slope, or not regression, excuse me, we're going to construct a confidence interval on slope. All right, let's do this. Remember, when we're doing confidence intervals, we can go through randoms. We're just going to be missing the H and a p-value, right? We're not going to have a hypothesis. We're not going to have a p-value. We will essentially have a test statistic, right? We're going to have our calculation of our confidence interval. So we can do this. So first of all, I'm going to see what we're going to do. We will construct a 99% confidence interval. for the true slope of the regression line relating number of Mentos and if I wanted to get super extra, I could actually write what that regression line is, right? It's going to be y hat is equal to 0.07807. Come on now. 083 x plus 1, yeah, 0.0. That's our regression line, right? Which tells us that for every additional mento that we put into the bottle, we expect for there to be, we're in ounces, I believe, 0.0803 additional ounces expelled from the bottle. Okay? So interpreting our regression equation, I think that's extra stuff. They're asking us to construct a confidence interval. We wouldn't have to do that, but it's kind of nice to do, to think about the problem. What we really need is the standard error here. So the standard error of our slope is this guy. So we need to go to our formula for that. So we will have our slope b plus or minus our t star value times our standard error b. Okay. And standard error is already given. The cool thing about this is there's a formula for that, right? So you have your standard deviation divided by standard deviation of x times square root n. Sorry, standard deviation of x times the square root of n minus 1. We don't really need that for this because we've been given what the standard error is. So this is going to be, but it's nice to have. So b, our slope is 0.07083 plus or minus, and now we need a t star value. How many entries do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2, 24. So n equals 24. So my degrees of freedom is going to be 24. Remember, degrees of freedom for our slope is n minus 2. So 22 degrees of freedom. We need to find our t star value. There we go. We got table D. We have our t distribution table. All right, so we're looking for 99% confidence. And our value, so let's see, let's get it all in frame there. So I said 22 degrees of freedom. And we are looking at 0.01. Is that lining up? Is that lined up perfectly? Okay. 2.508 is our T-star value. Right? So I'm saying, hey, 99% confidence is at 0.01. I do believe that that's also. So I should not be looking here, sorry. We're looking at a different spot than we would look if we were trying to get an alpha level. Right? So that is actually going to correspond with 2.81. And my standard error of my slope is 0.01228. We're going to calculate this thing, and I'm just going to save a little time. Calculated. So there's our interval. So let's interpret it in context. And again, lots and lots of writing. We are 99% confident that the true slope of the least square regression line relating number of Mentos and ounces of water dispelled is attained. In the interval. All right. Now let's interpret this. We would like it to be the case that more Mentos equals more ounces displaced, right? Is that what we think in our original problem? We gotta go back. Will more Diet Coke be expelled when there is a larger number of Mentos? So let's answer that question. Was, based on our data and our inference that we performed, do we have evidence to show that more ounces were dispelled when there were more Mentos? Well, it looks like our slope is always positive in our interval. Yeah, 0.03. Thank you.
And also time zero.
Some clever erasing there. And that's a 6. That was awful. Okay. So our slope is always positive. Not super positive, right? But always positive.
Yeah.
So that gives us evidence that when you put more Mentos, there are actually more ounces of soda dispelled. Fantastic. Super. Let's rock a t-test. Oh my goodness. I got so into this. And it's a good thing I went through and thought about it before I continued. We're about to go on a t-test, and I thought, did I ever once check conditions? And I did not. Huh? I know. No, it's not. It's not big enough. So let's go ahead and check conditions as an afterthought. And at least it's been done. So L, is the data linear? The data appears to be approximately linear, right? We can tell from the regression, from the residual slope. The residual plot. I don't see any nonlinear patterns. All right. I. Independent, right? I almost wrote independent with 2 I's. And we're also looking for large counts in this one.
So a non-linear would be like curve.
Yeah, you'll see. Yeah, so for nonlinear, you'll see something. If we have our residual plot. And what that's going to translate to is you're going to have some regression line, right? And it's going to go. You're going to have a bunch of. You're going to be trying to fit. There's going to be data above over here, right? So, right, these up here are above your line, and then there's a bunch below your line, and then it comes back above the line, right? So it's going to look, yeah, so it would match something more like that. Right, so that's roughly what's going on with that. Are our counts large enough? So each trial is indeed independent, and our number of Mentos, or number of trials, always put this inequality in the wrong direction. It's kind of weird to say that. Strange to talk about the number of trials that you should do with franchise. I'm actually curious. Right. N for normal. So we've got a histogram for our frequency and our residual that does not show any skewness or outliers. Okay. Then so the pattern of our scatter plot shows that standard deviation was approximately. And then our random, the data comes from a random sample. All right. Now I got full credit on it. It's a good thing I didn't move on without checking conditions. Wow, that is a lot. Sorry, you need this. So let's begin performing inference on slope using a t-test. T-test for the slope. Our test statistic is going to be our slope minus our hypothesized slope over standard error of our slope. Right? And we are going to be testing the hypothesis that our slope, that our parameter for our slope of our regression line is equal to some hypothesized parameter. So we'll find our p-value using degrees of freedom equal to n minus 2. These can be one-tailed or two-tailed. And I don't need enough. Okay. I remember there was something that I needed. Okay. You have a problem just to try out. And I think that this is going to be best saved for our next meeting. Because